team number 20. I'm Jordi and Gillio. These are my partners, Caicedo, Vega. And today we'll talk to you guys about the 2016 Shell Eco-Marathon chassis advised by Dr. Andres Tremante. Our project description is to design and manufacture a safe and efficient chassis design for the 2016 Shell Eco-Marathon battery electric vehicle. Team C will be also working with us designing and manufacturing the vehicle for the competition. Our problem statement is that highly efficient vehicles are growing in popularity and innovation is also on the rise. Construction of aerodynamically and ergonomically sound lightweight chassis is the key element in efficiency. In addition to efficiency, the driver safety is also a very important concern, so the design must keep all occupants safe in case of an emergency. Our motivation, of course, is to help represent FIU in the 2016 Shell Eco-Marathon with a battery electric vehicle of our own design, to gain experience and learn skills manufacturing and also designing a vehicle chassis, and not only to create a lightweight and efficient chassis, but to also keep in mind our safety of our driver. Our objective is to design, to model, and also to construct the chassis, including the structural frame and the roll cage of the Shell Eco-Marathon vehicle. The design and optimize the chassis while keeping aerodynamically and efficient body shape and stability of the vehicle, and to also keep the driver safe and all internal components in a case of an emergency through safety-minded chassis design. My partner, Andres Caicedo, will give you guys a better knowledge of the chassis design and analysis.
Hello, we're going to talk about some of the design alternatives we have for this project. Here's our first body. As you can see, it's a very wide body. The idea came from a go-kart, just a standard go-kart with a wide body. And our second design came from an NHRA dragster, those big long race cars with a big engine at the back. This idea was more appealing to us because of the narrowing of the body at the end. It's able to fit a more aerodynamic body on top of it. The go-kart was just too wide. It's too much surface area exposed, which increases our drag, which is something that we cannot have in a race car. We also have a square roll cage as opposed to a round bar. That is because at the university we don't really have the ways and means to manufacture it, so we would have to outsource it. We could do that, but that increases our total cost. As we will see in the simulations, we added a triangular member to help support the load of the actual roll bar. This is the final design that we came up with. There are two notable differences. The first is this member down the middle, the T formation. We did that to support the weight of the driver and the weight associated with it. Without it, the driver's seat would be dragging on the floor, and we can't have that for many reasons, including safety. The second one is this front structural member, the axle. The rest of the body is comprised of 1-inch tubing. This front member is 3-inch tubing. Now the reason we did that is we want to fit components inside the tube so that they're not exposed to the elements and increase our drag. We want to be able to fit brake lines and steering lines in there. The simulations, the testing we did were 700 Newton test, which is about 150 pounds, and that is done on the roll bar. This was the first design that we had, and as we can see, a huge deflection, which is the reason we ended up adding the triangular member for support. As we can see here, the triangular member increased, it lowered our deformation by a factor of 10, and that is why through our designs we incorporated that triangular member. This was our final body. These are the analysis on it. We can see a very low deformation and a high factor of safety for a vertical test of the 700 newtons. The Shell Eco-Marathon guidelines state that it has to deform, or it has to not deform when 3 tests are done on it, and that's from the vertical loading, then it has a horizontal loading, and then it also has a side loading, which we're going to see all 3. This is the second loading when you're pushing on the actual roll, on the roll bar. We have a high deformation and a low factor of safety. The event in which this crash simulation would be encountered is a head-on collision in which the cage bends. We don't foresee this in competition. There are many safeties incorporated in the final design of the car and in the race itself. Vehicles can be too close to each other, and it's also a closed course. And this is the final testing done from the side. It's pushing on the side. As you can see, we have a low deformation again and a high factor of safety. This is a comparison of materials. We initially had 3 materials. We had steel, aluminum, and copper. The reason we didn't go with copper, even though it appealed to us because of the cost, it's not a very structurally sound member. So in the end, we ended up with steel 4340 and aluminum 6061. As we can see, the steel is very rigid. It didn't deform as compared to the aluminum. The analysis we did all 3 at the same time. Front, side, and pushing forward on it for both the steel and the aluminum. As we will see for the factor of safety, the steel was very safe as compared to the aluminum. The aluminum is still safe. It's higher than a 1. It's a 1.2. The car didn't fail. And because of this, you may ask, so what material did we choose at the end? At the end, we decided not to go with the steel. It may be a little safer, but the reason is this number right here. The total mass of the car would be 166 pounds. That is way too heavy for a chassis. There is no way to be in the competition, to be competitive, and to have a friendly car. Because of that, the weight for the aluminum would be 29 as compared to the 166. That is the reason why we ended up going with the aluminum 6061. And now to talk about the design experience, Mr. Rick Vega.
Hello everybody, I'm going to speak about our design experience while designing this chassis. The standards we used, especially in the SolidWorks simulation, is the American National Standards Institute Standards, ANSI. We used that for the SolidWorks simulation and modeling. We also kept in mind the SAE standards, specifically the extruded aluminum 6061 standards. We followed those in order to get the parameters for our used aluminum. We also kept in mind the Shell Eco Marathon safety standards, most specifically Article 26, which describes the chassis/monocoque safety and solidity. The environmental issues that we wanted to keep in mind while designing this vehicle is that in general electric vehicles are incredibly environmentally friendly to begin with in daily operation. The vehicle is 0 emissions, and the only environmental considerations that we truly had to keep in mind will be that from the used components manufacturer, such as the aluminum, and the grid supplied energy which we would be plugging into the mains. The environmental aspects that we wanted to keep into consideration, electric vehicles are gaining a wide presence in the economical economy, as well as car manufacturers are adopting new technologies all the time regarding these. Companies such as Tesla, Chevrolet, and Nissan all have completely battery electric vehicles that are catching consumers' eye. The low cost and operation of these vehicles are extremely attractive to customers, as well as the tax benefits granted by the United States government for the use of these vehicles. Shown here is a simple chart showing the operating cost of a gasoline vehicle versus an electric vehicle. As you can see, the cost is way down with the electric vehicle. It's very attractive to consumers. Global awareness and perspective of our chassis and its constituent parts. Electric vehicles enjoy an already high level of overall awareness in the public, especially in the United States, with companies such as Tesla and Nissan and Chevrolet coming out with these flagship vehicles and catching public attention. Safety vehicles and stability is a very widely recognized thing as well. Many purchasers of vehicles are very concerned about the safety standards of the vehicle, how safe it is for their families and children. However, neither of these fields have yet been considered fully developed or perfected. So any changes or innovations in these fields is a very welcome thing in these fields. In terms of lifelong learning, the knowledge of how to manufacture a lightweight and efficient chassis is a great experience in itself. It represents the real-life design considerations that companies and manufacturers have to keep in mind when designing new vehicles. For the division of labor and the project schedule, Mr. Andres Caicedo worked on the SolidWorks modeling and analysis of the chassis, as well as a portion of our report. My friend Jordi Gillio worked on materials and cost analysis. He looked at the different parts, different materials that we would use and saw which would be the most cost effective for us, as well as his own portion of the report. And I, Rick Vega, worked on the finance management and allocation of funds for both teams, as well as the presentation elements and my own portion of the report. And as seen in the next slide, our timeline. As you can see here, we're coming into December, and we are ready to finish our cost analysis and begin purchasing and assembling our parts. The conclusion of future work, we are very happy with our progress with this vehicle. Work has been very productive. We are now ready to completely finish our cost analysis as soon as we're done getting price quotes from companies for the aluminum, and order the parts and begin assembly. And the spring 2016 semester, we'll see the chassis built, and in collaboration with our other team, we'll complete the car, begin testing, and hopefully go and win that Shelly Co-Marathon. And now we have Q&A. Thank you very much.
Comments?
Does this car run in a straight line?
No,
No.
no. It goes on a track.
So how's it going to turn if you've got the front axle part of the chassis?
We want the actual, we want the lines to extrude a bit so that way everything is inside, but the actual turning arm is going to be a little outside. So it does give us that range.
So connected to the axle, the end of the axle, you'll have a turning arm?
It'll be inside the, it'll be inside.
Show it on
the
the screen, please.
Inside the member.
Show it on the screen.
Yeah, it'll be inside the member. So this right here is gonna be cut in half, or it's gonna have a hole so that the arms can go through and end out here. It's not
Oh,
gonna
okay,
be-
so
it's not gonna be
that's just
connected
like
to it.
It's a covering plate.
a
pretty much.
covering?
Yes,
Okay,
yes.
okay. That's it.
Yeah, yeah.
What's he going to And then I was going to ask you all kinds of questions about the weld strength of the axles that you created here. But if that's
It's
just a cover, it's a
It's just
cover.
a covering.
Okay.
Yeah.
Okay.
I have a few questions for you. If you're cutting out part of that, which is one of the main members of your structure up front, how is that going to affect the safety of the car?
Yeah, it's a good cut. It's not gonna be completely cut, it's just gonna have a slit cut so that the control arm can go in there and then be able to separate for the left and the right for the turn.
Right, you're still removing.
We are gonna have to
You're
do
no
some
longer,
more
you no
analysis
longer
for
have
it.
a cylinder as your structure there.
We're gonna have to add more, to do more simulations with that member being cut out.
Second question is, the top two bars that extend to about 50% of your roll cage, all the way back,
Yeah,
is there a reason why you didn't take that tube and put it to the tip of your roll cage that will prevent the buckling that you were seeing on one of your analyses?
yes, but it interfered with our body.
Interferes with your body.
Yes, with the body that's gonna go around it, with the shell.
Okay. And last, have you considered, instead of using, you said 6061 aluminum,
Yes, we
using 7075 or 7255?
The cost was greater, but we could consider it. 70-75, you said?
7075 gives you about almost twice of your main mechanical properties. And I mean, if it's very expensive, then I would agree with you. But if it's just a small cost to get that, you would increase the safety of your car.
Which one, sorry?
Aluminum
7075.
7075.
7075?
We'll take it.
That's a good point.
Definitely consider
That's a good
that.
point, yeah.
We'll have to check the pricing on that.
Yeah. Thank you.
Maybe he would like to sponsor us. Next question. I know, right?
We take cash,
Shell has
credit,
plenty of money.
check.
But we don't have it. But we don't have it. They have it. Any other comments?
In your simulations, how did you compensate for welding?
When you select the members, can you go to the next one? Yeah, it's easier to see, well, I don't know if it's that easier to see, but the weld points are instructed, so you tell SolidWorks that there's a weld here, 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 and here, and it shows you at the weld where it would be the weakest. There was a testing on the side where this weld ended up being the weakest weld, so it does tell you, it simulates according to the weld as well. It does take it into consideration.
Okay.
Now, sorry.
Oh, go ahead.
My question is with the testing. How are you going to go about testing the car, testing this? And there's another team that's doing the braking and the
Yes.
steering, right?
Yes.
Right.
Are you going to have to wait for them to finish and then do your testing? Or,
We'll at least
how's it
have to
gonna
wait
work?
until we have a seat, wheels, and brakes
Yeah.
on our car.
Okay.
But we expect them to finish those things in time for us to have plenty of time for testing.
We're working together.
They always say that.
Yeah, every semester.
And before the competition, we're running out of time, but yeah, that's the goal.
Can you move back to that picture? Have you thought of, I know you mentioned that using, creating an arc as your roll cage was more expensive just because you don't have that. But you're adding, have you considered looking at what that would cost versus the added material you're adding to add, to give your roll cage strength, right? You're adding 2 more beams. Not only is that cost, but it's also weight. And you now have 3 different failure points that you're adding to your system.
That's
Yes,
very true.
But it was, for the round bar, it had a lower factor of safety. And the thing was that we would still have to add a horizontal member, because with the weight, it'll shift. And since it's round, you know, the weight will distribute. So we would still have to add another bar so it wouldn't be weight. But to answer your question, it was that safe for the round one, for the 1-inch tubing that we have.
Now, the main reason for that square on the back is for roll prevention, right? Just in case it rolls. Why do you want to have it square and not just leave the triangle there? Just as long as that tip is higher than the person.
Because we want to, oh, sorry.
Well, the main thing is that the triangle, if we left it just a triangle, that would leave very little room for our driver. And also we have to consider that the driver also has a helmet, and there needs to be a clearance between the helmet and the bar. So in order to facilitate that, we needed to have a wider superstructure so he has a bit of clearance over his helmet.
The dimensions aren't really specified here, but the car itself is not that wide. It's 80 centimeters across. It's like 2.5 feet, almost 3 feet.
You mean a triangle like this or the other way?
Right, like, if the only purpose for the box on the back of the square was for roll.
Yeah, for safety as well.
Right.
You can hit your
But
head.
if the triangle was big enough,
Then you have more height.
then you have more height, which you already have it there, and you get rid of the 2 or the 3 extra sides of
Oh,
that.
you mean, okay. Yeah, we can always optimize the design. Is there any limitation of the height there?
Yeah, there's
Remember
a
that?
limitation of 90 centimeters.
Okay.
And
That's
we're
a
at
constraint.
85 for height. And we still have to consider the body.
Yeah.
So there is a limit.
Yeah, but that's a good point. Maybe the height would be a constraint to change that design in a sense.
Do you look at any torque concerns? If somebody hit that rigid section that's supporting your axle, would the side,
This one,
yes.
if it hits from the side,
No,
it
if
shears
you
it
hit
off.
the front, if you hit on the front of it,
This one, and hit it back?
yeah.
No, we did not do those considerations, because it would be good for rider safety, but for race competition, they only care about the roll cage, about the roll bar.
I mean, that is something we would most likely have
We
to
could-
consider once we actually decide on how our steering system will fit in there completely.
Because, I mean, if that wasn't rigid, at least it would collapse on itself.
That's true.
That being
The body-
rigid, you're gonna take that load right into that side and twist this thing.
Well, the body itself should protrude, and it's gonna have a foaming at the end of this, but we can still run some analysis here.